Okay, so we are now going to take a look at the 4.2 classwork problems. Folks have had a chance to work on them in groups, so let us turn our attention to 4.2 number 1. And if memory serves, that's going to be Team I don't know. So Team I don't know, let me first turn on screen sharing. Oh, I did. I turned it on this time. I remembered. Yay. Good for me. So walk us through what you got.
Okay, cool. So we were using only analytic, i.e. by hand methods. Find the general solution, YT, for the following differential equation, which is...
You're so mean, Quentin, making him talk. You know he doesn't feel good.
Right here.
I mean, I can talk.
John's just like, he's got a bad headache right now, so he's coping.
So we used S and found, used the quadratic formula and found this lovely number.
And that's essentially our eigenvalue, right? If this were a matrix problem, we'd say, hey, we found our lambda values. But this isn't, we're not dealing with this as a matrix. This is just straight from second order differential equation. We're finding the homogeneous part of the solution. Proceed.
And using Euler's method, we found this.
Okay, my only thought there is you're missing some parentheses in the exponent on that line just below the cursor. You see where it says e to the, that s value, the -1 plus or minus I root 15, all that should be in parentheses because it's all of that times t. And that's how Euler's method or Euler's formula works on the line below. And so you're absolutely right on the line below.
Okay. And then we got the particular solution we're doing here. And that's why double Y. And then we plugged it in and we found alpha. And then we plugged that in. That's as far as we got.
Cool. So the very last step there is you've got your particular solution, which is -I/8 times that the cosine and the sine thing. And really, which part of the solution do we care about for the particular solution?
The real part.
The real part, because our forcing function, way at the beginning, our forcing function is a cosine. So the real part of that, when you multiply the I/8 through, is the sine part of it. And you've got -I/8 times I, so that becomes -I times I, which is +1. So the only other thing I think that you might be missing is there's a 1/8 out front. The 1/8 doesn't get sucked into the sine. The 1/8 sitting out front is there. So inside it's still just 4 times t. Yep.
Gotcha.
Okay, so that's our particular solution. That's our y sub p. So now how do I get my overall general solution? What do I do to write my overall general solution?
Find the part we just got and the y sub h.
Yep. Put together that particular part that you just got with way up at the top, the y sub h. And those three terms, well, not the top, yeah, exactly, right there. That y sub h, the right-hand side of that, plus the thing that you just found is your general solution. So nice work. It's a pain in the butt to type it all in, but the nice part of it is once you've got it, you can go back and edit it. Like if you're like, oh, whoops, I forgot a negative. It's easier to edit this than it is to go back and try to color out something that you've handwritten. So nice work. Cool. So that's number 1. That's reviewing that lucky guess method when we're dealing with a periodic forcing function. Now, that only works if it's a periodic forcing function by itself. So cosine or a sine, that's it. That's the only way this works. If it's anything else, if it's plus something else, all bets are off. It doesn't work. So who had number 2? If I remember correctly, I think it was, were there 2 groups that had number 2? Oh yeah, that's the 2 groups that formed into the supergroup. The ABBA of differential equations, if you will. I don't know who the other Swedish people are, but I know Emma's part of it.
I'll represent the team that I've hijacked.
Go for it.
You had the best ideas here, so we'll let you take over.
Personally, I feel more comfortable with number 2, and so I'm going to go ahead and just spearhead that one, and then let my teammates take the harder one.
You just take that number 2. You just take a number 2. Don't,
yeah, that's my big plan.
We're not at all going to be bothered. The others can help clean up afterwards, after you take that number 2.
Yeah, exactly. All right, so here we have number 2. It's fun, it's nice, we can absorb it, look at it.
Mm-hmm.
So basically what we're given is this really nice graph. And we're asked a couple questions about it, 3 to be exact. The first one being, what are the approximate initial conditions for the 2 particular solutions? And so we concluded that this one was at the origin, and so it's probably at y = 0 and v = 0.
Okay.
And then we concluded that this one was, it looks to be roughly around 1, 1, and so that's what we said. It's easy enough.
So if you were to report those, like write those down, how would you write down the initial conditions for that?
Well, we had a little bit of disagreement, but we settled on 0, 0, 0, and 0, 1, 1.
Okay, so like an ordered triplet.
Yes.
Yep. Where the first number represents time, the second number is
position, and third would be velocity.
Okay, so you've got the y going in this direction and v going in this direction. So usually we consider the horizontal variable to be the first dependent variable in our phase plane situation. So rock and roll, you got it.
Sweet. So then B, what kind of driving force does the oscillator appear to have applied to it? Explain how you can tell from the solution curves. So we said, I lost my notes. Here we are. So we said that it's going to be a periodic driving force. And this is because if you follow the solutions, they both kind of end up in this same loop, which is just continually oscillating across the y-axis. So, and yeah, that was pretty much it. We just kind of looked at it.
Yeah, because we know that curves on the phase plane, curves that look like circles or ellipses, those are evidence of harmonic periodic motion, right? And if it doesn't decay towards the center or explode and blow up and keep going forever, then what you're seeing is harmonic motion that is just cosines and sines, right? So the long-term behavior of this thing must be cosines and sines. So, nice. And
then C, describe the long-term behavior, cosines and sines. We said that because both y and v. We said to be oscillating, and that's because the driving force is oscillating, and then the driving force always wins. So, yeah.
Yeah, as long as there's damping, the driving force is going to win, right? So if I pushed and said, okay, but I think you can give me a quantitative view of what's happening with y and v. So what is the long-term prognosis for position? The position of this oscillator will, in the long run, be stuck between what position values, roughly?
Looks like about 0.5 and negative 0.5.
Yeah. So in the long run, this thing is going to oscillate between negative 0.5 and 0.5, whatever the units are, we don't know. And its velocity is going to oscillate between what and what, roughly?
Roughly -1, +1.
Yeah.
Ballpark.
Yeah. So just from this one phase plane graph, you can get 2 initial conditions that in the long run, both head towards the same long-term behavior. Because it doesn't matter where you start. If you're a harmonic oscillator with damping, the damping part of it means that the natural response just goes away. And all that matters in the long run is our forcing function. And in this case, it's pretty clearly an oscillating forcing function. Right? So nice work. Good job on that.
Thank you.
Yeah. How about number 3? Number 3, the egotists and Team Brat.
Yeah.
Oh, we had two. We had two. So here's what we're going to do. I'm going to have, let's have Team Ego give us what they've got so far, and then Team Brat, you can comment as we go and say, oh, we did it slightly differently. Sound good?
Okay, I'll share my screen. First we found the spring constant because it wasn't actually given. It was just, there was just a picture that showed the stretch under a given force. So
You
to
were able to,
calculate it.
and you were able to do that by using what? What do those numbers represent?
These numbers, so the 0.234 is the mass in kilograms. Oh, and I just realized we forgot to multiply it by acceleration to get the force.
Yeah, because the spring constant
So-
isn't mass over distance, it's force over
It's
distance.
force. Yeah.
But the nice thing about
this
the
should be
Maple
multiplied by
document is
4.
it's easy to fix, right?
So it's 9.8, right?
9.8, yeah.
And we divided it by the amount of stretch, which looked to be about 0.235 meters.
Okay. And so not surprisingly, it's about 9.8.
Yeah.
Roughly. Does that look about right compared to what you guys got? Team Brat?
Yes.
Yes. Cool.
Well,
Alright.
we didn't assume that it was in centimeters. We assumed it was in meters. So we,
Ooh, interesting. Yeah, because notice there's no units given on the distance. So yeah, I probably should have specified that it's basically a centimeter ruler. And as soon as I say that, you're locked in. But you could have interpreted it however you wanted. But okay.
All right, and then we just wrote our equation out, taking the new mass and the damping constant, and this would also change to the new value we just got. So that would be 9.76.
No. Leave it as a fraction.
Okay, yeah. 2, 3, 4. Oops.
So this came up a couple of times in for a couple of teams in the investigation. If you're given the opportunity to use exact values and not do rounding, don't do rounding, right? Think of it this way. It's like if you're in a chemistry class or a physics class, you don't actually plug in the numbers until the very end of the problem. So if you're going to plug in the numbers early on, which is fine, Maple can handle them as exact values. And when you're ready to round, you can round. But don't round in advance, because every time oh, I'm just going to round that off. I'm just going to round that off. You keep doing that, you're shaving off precision along the way. So, yay.
All right.
So what happened?
All through here, because it wanted us to solve for the function,
So
we
that's
started
gonna
doing it by
change.
hand. Yeah, this would all change, but
So if you scroll down, because I didn't ask you to do this
we
one
just
by
do it
hand.
yourself.
Yeah.
Yeah, so this would be 9.8, and I believe everything else is fine. Oh,
Required indication of the solving variable.
um,
Oh, I think you need YFT.
so should I change these to the?
Yeah, do a second derivative on that one.
I don't think you necessarily need to do that. I think you need to specify that it's a multiplication between your 0.234 times 9.8
Times the Y. Yeah, I think that's the problem.
Yeah.
So that
I think it
multiplication was okay.
Oh, so
Yeah.
There, right there.
Yep.
so should I put these in parentheses or?
Just do
Just
a
a little-
multiplication.
Oh, okay.
Yeah, Maple's pretty picky about that. And so do, just for giggles, just make that one dy dt.
Right.
And then change that one to YFT. I think you'd be good. Uh-oh, still doesn't like it. There's
Do the
something.
same
Oh, I know
multiplication.
why. I know why. It's because I
1.1.
declared it as a variable later on.
Oh, okay. There we go. Now notice, ugh, if you had to do this by hand, ugh, but notice Maple gives you exact values. It doesn't mess around with trying to, you know, round those off because it leaves it up to you where you want to round it. This is the particular solution that you can now use to make predictions. By the way, does that look about right comparatively compared to what you guys had? I know it's kind of like, oh, it's a big honking mess, but Team Brat, does that look about right? Did you have 1,
Yes.
2, 3, 4 terms, 2 cosine terms and 2 sine terms?
Yes.
So it's worth noting that you have 2 of these terms have exponential decay attached to them, right? The first 2 terms, you see it? Yeah, there it is. There's an e to the minus some junk times t in those first 2 terms. The last 2 terms, there's no exponential decay. It's just cosine, and the other one is just a sine. And there's constants sitting in front of them. What does that tell you about where you can find your natural response part of the solution and where is your steady state part of the solution?
So the steady state would be the last 2 terms, right?
Yeah. In other words, that's the stuff that even long after the natural response has died down, that's the stuff that sticks around. So we expect in the long run, those first 2 terms are going to go and taper off to nothing. Because as t gets bigger and bigger and bigger, those just head towards 0. But the last 2 terms, those don't head towards 0. They just go wobbly, 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 wobbly. So how could we verify that that is actually what happens?
Mm. Can we take a limit or?
You could do a limit. The problem with taking a limit of a cosine or a sine is it's going to say between here and here. It's not going to, there is no limit per se. But taking a limit, that's more of an analytic approach. Another way you could do it would be a graphical approach. So what if you just said plot and then write RHS of number, whatever that one is, number 4?
Do I just do a
Yeah, parentheses, and then control L,
control?
and then 4, the previous line, yep. Then close parentheses. And then, yeah, there you go. Sure enough. Now, we don't care about the stuff that's negative time. That doesn't matter to us. All we care about is the stuff that's everything from t forward or t equals 0 forward. And so, oh, you're doing it the fancy way. Look at that. Yeah, and the vertical, obviously the vertical is, nothing. We hardly need any in the vertical direction.
Well, let me change it then.
Yeah, there you go.
So like negative 1 to 1.
Yeah, I think it's probably even smaller than that, but let's see. Hey, look at that. And if you extend the time out, you're going to see a nice, there you go, a nice, oh, it gives up after a while. It's like, I don't want to draw this. For some reason, it dies off. I don't know why that is. That's really weird. But if you were to, in the actual command of the plot, after the right-hand side, if you do, after that first close parentheses, if you say comma, what would it be? Comma t equals 0 ... 20. That should give us what we crave. There we go. Now notice, in the long run, you have oscillation between a maximum and a minimum. But early on, those first 2 kind of a peak and a valley, those are not at the long run behavior. We're still seeing the effect of the natural response. So that first peak is not as tall, and that first valley is further down, right, than how it behaves in the long run. So that's where the natural response is still having an effect, but after that, it just kind of like, it gives up. The natural response is done. The damping has done everything that it needs to do, and this thing has fallen into a very predictable periodic pattern. Now, the one thing that I want to make sure is clear in looking at this graph, what you're seeing in the long run, that up and down, that wobble, that is not equal to 1.3 times sine of 2.5t. That is not the equation of the forcing function, right? You can pretty easily verify its period is different, and its maximum and minimum, its upper and lower amplitude values are not positive 1.3 and negative 1.3. So what you're seeing is the result of the harmonic oscillator falling into a steady state pattern with that particular forcing function applied to it. If you change the forcing function, you'll change the consequence. So real quick, do me a favor and go up and change that 2.5t in the desolve. Yeah, change that to, I don't know, call it 3.5t, just for giggles. Run it, and then let's do plot that same thing. Now notice what happens when he hits enter. It's not the same function, but you see very similar structure to this thing. Oh, in the long run, it still behaves like a wobble, 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 right? But initially, you've got that natural response that's kind of dying out over time, and the forcing function is just winning in the long run. So much winning, so much winning. So I think there was a part C and part D to that.
Yeah, so part C was just evaluating the position at 3.7 seconds.
Okay, and so that is a different function than the correct answer, right? So can we switch over to what Team Brat had and take a look at their part C and part D real quick?
Yeah.
We did not get the right answer either because we messed some stuff up pretty similar to them. So
did you figure out what it was though?
Yes. And
Okay.
I did not fix it.
So what we can do is down there, right after C, the next line, just delete all that other stuff down there, and we'll do a quick fix. We'll just delete all that stuff, and then we can say eval, and then parentheses, right-hand side of 4. No, we don't want to eval the whole thing. We just want to eval the right-hand side of 4. Yep. Parentheses open, parentheses closed. Comma, t equals, what is it, 3.7? 3.7. And so it gives us the exact answer when we plug in t equals 3.7, which we can then approximate out to however many decimal places we want. So I just noticed there's something in the chat. Oh, how did the exam? Oh, that's from a long time ago. Wow, I'm really not paying attention to the chat. Anyways. So we have the ability to come up with a solution, evaluate the solution, and make any prediction that we want. If you said, well, I mean, based on the graph, where would you guess? What time would you guess this thing is reaching or it's coming back to equilibrium? Pick any one. Just guess. What would you think?
Well, like at 2.
Okay. So it looks like it might be a little bit past 2, but let's try it. Do the exact same eval trick. Let's try evaluating it when t equals 2. And you're like, oh, God, that's a mess. But notice, pretty close to 0. So you could go back and you could play around with it, tweak it a little bit, and say, well, what if it's just a little bit beyond 2, like 2.01 or something like that? And you could do this over and over. It's a way you could literally hunt for zeros if you wanted to. If you didn't feel like solving that thing set equal to 0, you could do it this way. Okay, so somewhere between 2 and 2.1, you know that it reaches a 0 value. So I know Chris is just going to go to town on this, and he'll probably spend the next 2 hours doing the hunt for the 0, approaching it from both sides. But here's the thing. This is how sometimes we have to solve problems, because I don't know if you noticed, the right-hand side of that solution is a mess. And if I said set that equal to 0 and solve for it, Ugh. Speaking of which, what would happen if you tried to solve the right-hand side of that thing equal to 0? Let's find out. Let's see what Maple tells us. So we're going to solve the right-hand side of number 4 equals 0. Or Roseville High School, number 4 equals 0. Well, sometimes Maple just doesn't do everything for you. Sometimes its solutions are not exactly the most user-friendly. And so having that alternative method of, hey, graphically I can see it's right around 2, and I think it's just a little bit bigger than 2, and within, I guarantee you, within 5 minutes, you will be like out to 5 decimal places of 0. It's well within our tolerance for measurement, right? Because remember, those t values, that's time. And if you're measuring seconds out to the 5th decimal place, I don't think you or I have a device that can possibly measure time out to 5 decimal places. Not accurately, not with that level of precision. So you can use this to your advantage. And then, of course, explain the long-term behavior of the oscillator. We already talked about that. So how you feeling about that one? A little bit better? Now notice, I didn't make you solve this one by hand because it's all, God, it's a mess. You don't want to do that, right? But there will be times when I say, I want you to solve this by hand just as proof of concept, like on the last problem, that you, or on, excuse me, on problem number 1, that you know you can do this if you solve it by hand. So thank you, sir, for sharing your screen. We have one more to take a look at. And it is literally twice as good as number 2.
Okay, Stephen's going to share his screen, and I'm going to try to explain. But we got stumped, so.
Oh, excellent. That's my favorite type. Excellent. So what do you got?
Okay, so, well, first we desolved it just to see what it would come up with. And it came up with stuff that looked very complex. So
well, complicated.
We were kind of looking at it like we were trying to follow the first one, or number 2 on 4.1.
Okay.
And we were trying to split it up into G of T and H of T. And we kind of figured that maybe G of T was cosine 4T and H of T was 2. Wait a minute, let me find that problem.
Well, just for the record, does any of that look familiar to Team Humble? Not Team Humble, Team Ego. Who had this one? Who had number 1? Sorry, Team I don't know. Does any of their solution for that differential equation, does it look familiar to you?
All of it but the plus 1/8.
Do you recognize it? That e to the negative t times sine root 15t times a constant, plus the second term with the cosine times a constant. Those 2 terms, that's the homogeneous part of the solution that they found. And then the 1/8 sine of 4t, that's the particular solution that they found. And the equation that they solved was almost identical. The only difference was they didn't have a plus 2 on the forcing function. Oh, it faded away. Yay, okay. So their forcing function, this is fun. Yeah, their forcing function was just the cosine of 4t. The forcing function for this one is cosine of 4t plus 2. So this is where I'm asking you to put your thinking caps on and connect with that little piece of homework that I had you do after last class.
Yeah, and so this is where we kind of got stumped.
Okay.
Because we weren't sure how exactly to do it this way. So we were like trying to solve for we were trying to make it like s² plus 2s plus 16 and solve for like the roots. And we came up with, hold on, what was it? -1 plus or minus 2 times the square root of, oh, hold it. -1 plus or minus the square root of 15. So we were kind of puzzled.
Times I.
Because,
Mhm.
Yeah, times I.
Yep.
But we were kind of puzzled because like the -1 like dropped out of like those sines and cosines.
Oh, yeah, the -1 that's sitting in front, the real part of our, if you think of it as an eigenvalue, the real part of our eigenvalue doesn't wind up inside the cosine and the sine. It winds up as the exponent of the e to the. You see it? There's the, oops, disappeared. There's the -1 right there. The root 15, without the I, is sitting inside the cosine and the sine, thanks to Euler's formula. And the -1 from the eigenvalue is sitting out front in the exponential.
Yeah, so that was another thing we came up with. Like, why do we have an e to the -t and a sine and a cosine?
Because you can think of this as the underdamped case, right? So it's exponential decay, but it's also oscillating.
Okay, so it's kind of a combination.
Yep. And so the line just above where the cursor is right now, right where the mouse is at, that's the key to this problem. And if you, on the other window, like I'm directing traffic here, on the other window, if you scroll up to section 4.1 and take a look at 4.1 number 2, just a quick reminder, that was the homework that I had you guys do last time, which basically said, if you want to solve this differential equation that has 2 terms in its forcing function, thinking backwards, you could solve each one of those differential equations with 1 term as the forcing function, solve that, solve the other one with the other term as the forcing function, solve that, and then just add the particular solutions together. They're going to have the exact same homogeneous part. So the e to the -t times sine of blah, blah, blah times a constant plus the second term, e to the -t times cosine, that part of your general solution is going to be the same whether the forcing function is a cosine of 4t or just 2.
Okay, that makes sense.
Right? So we're making use of that problem that you guys all solved, number 2, to be able to solve this one and say, look, all we have to do is solve the homogeneous part of the solution and then use cosine of 4t as our forcing function, find the particular solution for that. And then go back and say, use 2 as the forcing function, find a particular solution for that, then add those 2 particular solutions together, and indeed that's exactly what you get. The particular solution. Go ahead,
so we should have pretty much done it twice almost.
Yeah, I mean that's the way to do it. It really is. Because we don't have a way in this section, we don't have a way to incorporate a periodic forcing function with some other term, right? We don't know what to do with that. We can't use Euler's formula with that because it's a cosine, but then there's this other term plus 2. What am I supposed to do with that? Well, the answer is you can't use our lucky guess trick, right, from section 4.2. But you can take each one of those forcing functions in turn and find their particular solutions.
Okay.
Yeah.
Okay, yeah, we got stumped on it, but I think it makes sense now.
Oh, that's okay. I again, this is practice. This is like seeing that, special pitch for the first time. You don't want it to be in the middle of a game when everybody's counting on you. You want it to be in practice when you're like, oh man, I totally struck out, but I think I got an idea what I can do to hit it next time, right? So recognizing this as sort of a special situation, right? Of course, Maple can solve it for us all in one fell swoop. We can desolve it and get a solution. But that solution comes from what we did in 4.1 and what we did in 4.2. So we don't have tons and tons of time, but that gets us through the classwork for 4.2. So what I definitely want to do today is finish up the 4.3 notes. So right now, any questions on the 4.2 classwork at this point? How are we feeling about that? Okay. Tired already? Really? It is 7:15. Yeah, it's getting to be that time. Everybody's gonna have to yawn collectively. Now, whatever you do, don't yawn right now. It feels so good to yawn. Yes, I got one. Oh, excellent. Some people are really, really easy to trick into that. Other people are just like, I don't know where you guys fall. So what we're going to do right now is turn our attention, if I can figure out how to get this chair to move, we'll turn our attention to the notes for 4.3. If you remember the last little chunk of notes for 4.3, we had a situation where we had an undamped harmonic oscillator. So there's no damping term. And we had a forcing function with a parameter for a frequency, right? Or essentially a frequency. So this thing right here, we don't know what it is. It could be anything. And we went through this process and solved and found out that our general solution, look like this. The first two terms are the homogeneous part of the solution. And so you can see the homogeneous part, this thing is undamped, so it's just going to keep oscillating forever. If there was no driving force, that's what it would look like. But because there's a driving force, that means that we also have a particular part of the solution, which is this. And this thing right here is interesting because it's another cosine term, but it's not the same frequency as this. This is our omega. But this term sitting out front, 1/2 minus omega squared, that's problematic because you can plug in any number you want for omega except
Square root of 2.
Because if you plug in the square root of 2, you're going to be dividing by 0. It's not a problem for the cosine. It's a problem for this thing. So if omega equals the square root of 2, the universe breaks, there's a hole, and everybody falls in and we all die because you're dividing by 0. But this actually has some real world implications. And so what we're going to do is play around with Maple. And again, we're going to do this pretty quick and dirty. I just want you to see what happens when we try to do this in Maple. So let me do a new share with Maple. Where's Maple? There's Maple. And my mouse is being really funky tonight. Okay, so all I do with this is I just do a copy and paste. So I set up my initial conditions, I set up my differential equation, and I start with a specific value of omega. I just want to see what happens if omega is 0.6, which is nowhere near the square root of 2. And if I do that and I take a look at the plot of my solution, this is just over from 0 to 50. And you can see it kind of looks like it's jumping all over the place, but there's a little bit of a pattern there, kind of going up and it goes down. It's kind of hard to see. If you went out further, maybe we could spot if there's a pattern to be seen there. It's kind of hard to tell. But what I can do is go back here and just copy and paste all this junk. Seriously, mouse? I don't know why my mouse is being so possessed today. It really does not like what I'm doing. So all I'm going to do is I'm going to change this now. I'm going to call this, come on, I'm clicking. There we go. ODE2. And I'm going to change my omega to something a little bit bigger. I'm going to go 1.0, right? Again, it's not the square root of 2, but it's getting closer. And so if that's what I got, you'll notice my ODE changes. And when I desolve this, my ODE2 is going to produce a solution that looks like this. Now notice, it now only has 2 terms. There's a cosine term with root 2 as the frequency and one with 1 as the frequency. And so if I plot this thing, oops, I just changed the name. That's the problem with doing this. If I plot this thing, you get something that still kind of looks like a mess. If I only go out to 50, you can, is that the same damn thing? Why is it giving me a hard time? It should be producing a different curve. Come on, Maple. Yeah, okay. So we can paste it one more time. By the way, the other way we could do this would be use the explore command. The problem with the explore command is you only have a range of things that you can allow it to be. What is the square root of 2 as a decimal, roughly? Anybody know?
1.414, I think.
Yeah, it's a 1.4. So I'm going to do 1.4, which is pretty close to the square root of 2, but not exactly the square root of 2. So I'm going to call this one ODE 3. And this will be Y3. So let's solve this thing. Notice we now have a cosine and a cosine, different frequencies in there, right? Different arguments. And so if I want to plot, come on, Y3 from 0 to 500, I get a very different picture. When I get close to the square root of 2, I start to see something happening. Now, if I kind of zoom back and say from 0 to 50, it looks like I have oscillation, but the amplitude is increasing. Notice the period of that oscillation doesn't seem to be changing over time. It's still about the same distance horizontally, but the amplitude is growing. And as you saw when I had it from 0 to 500, you can see that it grows, the amplitude grows, and then it reaches kind of a maximum amplitude somewhere out here at about t equals, I don't know, 210, 220, something like that. And then it goes back down, and somewhere around 450-ish, it looks like the amplitude drops to almost nothing. This phenomena, the thing that we're seeing right here, and if we extend it and go further, we can see what happens. This phenomena is called beats, and not the ones by Dr. Dre. These are actual beats, and actually pretty good beats, unlike the ones by Dr. Dre. These are, please don't sue me, Dr. Dre, if you see this on YouTube. These are beats that happen as a result of being really close to the forcing function frequency and the harmonic oscillator natural frequency. They're really close to being the same thing. So what happens when I throw, instead of something that's close to the square root of 2, what if I just go for it and make it square root of 2 inside there? What do you think is going to happen? Well, it looks like our particular solution is now just a sine function. That's kind of weird. It's just a sine function with a frequency, essentially, of root 2. But it's a sine function times something else. Do you see it? It's a sine function over 4 times the square root of 2 times t. So it's like taking a sine curve, which you know is just wobble, 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 and multiplying it by something that grows linearly. As t gets bigger and bigger and bigger, this second part of the equation, this part right here, that's going to get bigger and bigger and bigger. So you're taking your sine curve, that wobble, 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 and you're just multiplying it by something that gets bigger and bigger and bigger and bigger, and it never gets smaller. It never comes down the other side. So not to surprise you at all, but what we have is something that just keeps growing and growing and growing and growing. As a matter of fact, you can actually ask Maple, you guys already know this, you can ask Maple to plot this thing from t equals 0 to infinity. And Maple says, okay, I'll do that. And looking at what it tells you, you have, it's kind of hard to make out, but right there on the t-axis, it lists infinity as the value of time right there. And you can see that at infinity, this thing is at plus and minus negative infinity. This thing increases in amplitude infinitely large over time. Now remember, this is a harmonic oscillator. Can the harmonic oscillator increase to an amplitude of infinity in terms of its oscillation? I'll let you think about that for a moment. Whether it's a mass on a spring wobbling back and forth, or a little kid pumping their legs to swing higher and higher and higher, or whether it's a building that wobbles when there's a breeze. If we tune the forcing function to just right, this thing is predicting that we will have infinitely large amplitudes of oscillation. Well, since infinity is a direction and not an actual location, what does that mean for our harmonic oscillator if we tune things just right for the forcing function? I think my headset's broken because I can't hear you. Really? Did everybody just like go out for a hamburger or something? What's going on? Did you all agree we're just going to sit there and stare at him while he looks like an idiot? That's really sweet. Thank you. I really appreciate that. What happens since we have a harmonic oscillator that is wobbling with increasing amplitude and it doesn't appear to ever want to stop increasing? What's going to happen to my harmonic oscillator?
Just gonna break the model.
Yeah. Even if you're on strike, you know that. It's going to break because no physical reality can have infinitely large oscillation. So whatever the harmonic oscillator is, whether it's the kid with the swing or the building with a breeze that's blowing at a particular frequency, or whether it's a harmonic oscillator, just a mass wobbling back and forth, if you drive it at just the right frequency, you will wind up with an increase in oscillation that breaks it. And the trick is, if you were to use a frequency that is close, but not exactly, you still wind up with major increases in oscillation. Look at the amplitude values. The first amplitude values were just a hair above 1 max and -1 minimum. When we got a little bit closer, it jumped up to almost 2 max and -2 minimum. And that was not exactly right next door to the square root of 2. It's a ways off. We got even closer. We said 1.4. Take a look at what happened to the amplitude. Yeah, the beats are there, but look at the amplitude. We are now in the neighborhood of an amplitude of 50, literally like over 50 times the amplitude when we started with it, nowhere near the square root of 2. So the problem that we run into is you don't have to be at what we call the resonant frequency with your forcing function. You don't have to be at it. You just have to be near it to get this effect of massive increases in resonance. These beat frequencies, you'll notice here, these beats are a ways apart, but it's measurable. And as you get closer and closer, you wind up with something that heads towards an infinitely long beat frequency, because there's It just never comes back down. The amplitude just increases. So you don't have to be close. This value doesn't have to be exactly equal to the square root of 2. It just has to be nearby. And it will break your harmonic oscillator, no matter what it is. So thinking about our, let me do if I can stop share. There we go. Thinking about our harmonic oscillator back on the notes, back in notes land. Where the hell is it? Are you guys seeing the notes? I'm not getting the boxed image.
I see your desktop.
You see my desktop? Oh, that's not very helpful.
Yeah, it's like a tiny box.
Let me see if I can figure it out. My computer's being annoying. That should work. Did that work?
Yep.
Yay, okay. So we play around with this iterative process, and we just presume these initial conditions for convenience. But notice what we're presuming. We're presuming we start off with no displacement and no initial velocity. So it's like we have our mass on a spring, we just leave it set on the table, but then we turn on this forcing function that starts pushing and pulling and pushing and pulling and oscillating at whatever that frequency is, cosine of whatever that frequency is. So we chose those initial conditions for convenience. You could have picked any initial conditions and you'd get the same result. So down here, so what are some things that we notice about what's happening? So as our omega value from either direction approaches the square root of 2, we see some things happen. We approach resonance. Resonance is a state, right? You can be in resonance, but that would mean omega is exactly equal to the square root of 2 in this particular case. And so what does that mean? There's a couple of consequences for this. One of them is the amplitude of y of t increases dramatically. So as you approach resonance, the amplitude of your position function increases dramatically. Another consequence of this is that those beats, which are the oscillations within the oscillations, get longer between them, or get less frequent, you could say. So a longer beat period. Another consequence is that those beats get slower, if you think of it that way, in time. And higher in amplitude. And there's one more consequence. The frequency of the steady state component changes. And you might not have noticed this when we were looking at the solutions on Maple, but the frequency of the steady state part of y of t changes, but not the natural part, the natural response. In other words, as we tune our forcing function, it responds in terms of the steady state part of the solution. But tuning the forcing function doesn't change anything about the harmonic oscillator. Doesn't change anything there. So the harmonic oscillator has a natural frequency. You can't tune the natural frequency. It just is. But if you have your forcing function, the other side of the equal sign is your forcing function. And if it's periodic and you can tune it just right, then you can basically make it so that your steady state response has a massive amplitude, right? So where does this happen? Where do we see this happening in the real world? Where do we see beats in the real world? Or should I say, where do we hear them?
In music?
Anybody musician ever play in band or orchestra? Yeah, some of you I think have been. If you've ever had to tune your instrument at the beginning of a performance, everybody, you know, the sound of the orchestra tuning up, and people all trying to match pitches and stuff. How do you match the pitch? Well, one of the ways you do it is you listen for the beats. And if you can have fewer beats, then that means the two waves are closer to being in sync with each other, right? Smaller number of beats means closer to being in resonance with each other. Now, because this is a mathematical world that we're living in, the only way you can get infinite amplitude increase is by being at the natural frequency for your forcing function. But of course, there is literally no chance of that happening by changing the frequency manually. The fact that the square root of 2 is an irrational number means that there's literally an infinite number of decimal places that you'd have to match, which is not possible. So this has echoes in probability theory, but the probability of you landing exactly on the natural frequency for your forcing function is 0. You might be close, but you're not going to ever be exactly on it. But that's good enough, right, to do all kinds of interesting things. So on the next page, for our initial values, we can actually proceed to figure out what's going on with our general solution. So if we're looking for our general solution for these particular initial conditions, we're going to start with our general, which is y of t, and this is from previous pages. Remember, it's our homogeneous part, which is k1 times the cosine of root 2 t plus k2 times the sine of root 2 t plus 1 over 2 minus omega squared times the cosine of omega t. So this, if you remember, that is our homogeneous part. And this part is right here, our steady state. So that's our y sub p that we found from the previous page. So what we're going to do now is use our initial conditions. And if we use for y of 0 equals 0, that's pretty nice and neat, because when you plug in 0 into the sine function, you wind up with 0. So the left-hand side of this would be 0 equals k1 times cosine of 0 is just 1. So that's going to be k1 plus 0 plus 1 over 2 minus omega squared times 1. So that means our k1 is just equal to negative 1 over 2 minus omega squared. And the other initial condition that we have was for y prime. And I'm not going to go through and actually take the derivative of this. I think you guys in your heads can see taking the derivative of y. We're going to get a root 2 out front, and this will turn into a sine. This will have a root 2 out front, and this will turn into a cosine. So the fact that this turns into a sine means it just goes away. This is the only term that sticks around when we take the derivative and plug in t equals 0. And you'll wind up with something like 0 equals root 2 k2. And that means K2 equals 0. So for these particular initial conditions, we know K1 and K2, which means we can write our particular solution. So for those initial conditions, we have our particular solution of y of t equals K1 is this thing. So -1 over 2 minus omega squared times cosine root 2t. And K2 is equal to 0, so that term goes away. Plus, this guy right here is still around, 1 over 2 minus omega squared times cosine omega t. And hopefully you see there's a constant, or excuse me, there's a common factor of 1 over 2 minus omega squared. So I can simplify this a little bit, and I'm going to have 1 over 2 minus omega squared times, this is going to have a negative in front of it, so I'll put him at the end. It'll be cosine omega t minus cosine root 2t. So what do we see when we look at this? Well, hopefully when you look at this, you see two things. You see a periodic component, right? This gives the periodicity. And it is completely dependent upon what do you tune your omega to? What do you tune your forcing function? And notice, if this thing is square root of 2, then we have it minus itself. It just disappears. But out front, if omega is the square root of 2, we know we have problems. Because out front, this thing, this part, is serving as the amplitude. This gives the amplitude of the solution. So whatever you let your omega equal, that's how you determine your amplitude. So you tune your forcing function to a particular value for omega. You will have periodicity that depends on omega, but you'll also have amplitude that depends on omega. So a couple of points to kind of notice. Amplitude is not dependent on time, but it is dependent on the omega value. And just a reminder, the omega value is basically the frequency of your forcing function. So how much amplitude of oscillation there is in your solution depends completely on what did you tune your forcing function to. The other thing that's worth noting is the beat frequency. Is also omega dependent. And I'm not going to go into the weeds on the trig, sort of looking for identities, but there's a way to combine two trig functions that have different arguments to combine them together. And when you do, you wind up finding out that the beat frequency is equal to the square root of 2, in this case, the square root of 2 minus omega all over 4 pi. And so you can see where the square root of 2 is coming from. This thing right here, that's from the harmonic oscillator, the natural frequency. And this guy right here, the omega, that's from the forcing frequency. And so if those two values are really close together, if omega is really close to the square root of 2, the numerator on that fraction is tiny small, which means you'll have a very low frequency. And if you're thinking about waves, low frequency means standing in one place, you get hit with waves very slowly. Like they're not frequent. They're not hitting you frequently. So low frequency means longer period. And so if these things are further apart, if omega is really, really different than square root of 2, then you might have a relatively large beat frequency, which means you're going to get hit by more beats. The further you are from resonance, the more beats you're going to hear. Right? Does anybody, okay, this is going to sound like a weird question. Does anybody have and use themselves an electric toothbrush? Anybody? Electric toothbrush? Okay, we at least have one. If you've never had an electric toothbrush, they're so much fun because you put them in your mouth and you hit the button and it goes and it creates oscillations inside your head, and you can actually feel the oscillations right on your teeth, obviously, but it creates a sound too. And so, Bryce, if you have an electric toothbrush, I want you to try this tonight, and you're going to report to us on Wednesday what you found out. Can you sing or hum the same pitch as the toothbrush? And what happens when you get close to the same pitch, but not exactly the same pitch? Have you ever done that before? You know what I'm talking about?
I have not, but I do know what you're talking about.
You're going to try it tonight.
I actually have done that. I don't have an electric toothbrush right now, but I've done that before with like things like that.
Oh, it's so cool. You can wind up getting, if you get two pitches that are really close, but not exactly the same, you wind up with those beats, and you can hear like underneath the tones themselves, because what you're hearing is the beat frequency. So I've got a way of being able to kind of show this, but you're going to have to be patient with me. So you'll notice down at the bottom, if you're really interested in beat frequency, you can spend some more time on this. There's pages 416 through 419. If you're interested in acoustics or civil engineering when it comes to structures that might undergo periodic forcing, it's definitely worthwhile to check out. So there's, on the next page, there's a little bit more information about this. And it's just kind of stuff that we've talked about along the way. This phenomenon of resonance is what happens when you have these frequencies close together. But what I really want to do is take a look at some of these links. I want to pull up these links so that you can kind of see what's going on. And the one that I hope to show, and I'm hoping that this works, is I can do an online tone generator. This is a pretty cool one. I'm going to share screen in a second, provided I can get my computer to behave. It's really annoying. I think my mouse is dying, like the battery on my mouse is dying, and so it's behaving very strangely. Okay, so what I'm going to do is I'm going to share screen. I'm going to share this. Yeah, what the hell, you'll be able to see all the windows here. So you should see my online tone generator. I'm going to kind of bump up the size. Okay, it doesn't like changing the size. Fine, screw you. Okay, so if I hit play, I should be able to make it so that you can hear this. Audio settings. I got to change this real quick in the audio settings. Come on. Man, my computer is really freaking out on me. Can I include? Oh, it's driving me batty. Oh, damn it. Intermittent background noise. Damn it. I know there's a way I can do this. Okay, I'm going to try this. Okay, I have a feeling that this stupid mouse, this is not going to work. But let me try. I'm going to hit play. Can you hear that?
Yeah.
Holy cow, you can hear it. It worked. Okay, so on this window, I'm going to start playing the tone at 440 hertz. Literally 440 waves are hitting your ears every second. Does anybody know what note that is?
A, right?
Yeah, it's an A. So if I hit play on that one, and then I change the other one, I don't know if you can hear it, but I change the other one to 439 hertz. Can you hear it? That is 2 windows open at the same time, playing almost the same pitch. Now, if I change this to 438 hertz and hit play on the second window, faster beat frequency because we're further from the natural frequency. We're further from matching. And so if I decrease it a little bit more, you get this. Now that is driving me nuts because it's so loud in my ear. I don't know if it's loud in yours. Wow. But you have access to the links for that. And what I want you to do is check out the links, all the different possibilities for this. The links that I have on there. I want to point out that this gets used all over the place, from acoustics, obviously, to building construction and design. The Aeolian harp, that other link that I have on there, is actually a really useful one. If I can switch. Oh my God, my mouse is driving me nuts. If we go to the bit.ly link, 254 Aeolian harp. Oh, doesn't like it. 254. Is my keyboard causing problems now? There we go. Blah blah blah. Hey, good. We get to watch the ad. So this was an art installation that went in the San Francisco Bay area, down near the docks of San Francisco Bay area, and it's basically a series of metal cables tightened in a frame to different tightness. Can you guys see this as well as hear it? You can't see it? Oh, shit. Well, then what am I doing this for? Thanks for the heads up, everybody. Okay, hold on. Let me stop and share. Sorry, I had all this set up before, but then my computer died, and so I'm scrambling here. If I can change this, change it to the desktop. There we go. I can do that. So what we have in the background of this thing is, come on, mouse, please stop. There's cables connected to a metal frame, and those cables are all kind of tuned to different pitches. And when the wind blows across the cables at just the right speed, you wind up creating little eddy currents as the wind kind of blows along it, kind of gets split by the cable, and it sort of breaks off little eddy currents in the air. And every time it does that, it gives it a little bit of a push. And if it's just the right speed, you can see that it approaches this resonance. Whoops, it approaches resonance. And so it produces this super eerie noise. There is no amplification going on. What you're hearing is literally the wind causing vibration in these metal cables. And so the background story on this, I'll hit stop so I can talk. The background story on this is along the Ionian coast of Greece was a mythical settlement of the Aeolians, which it's named after the Greek god of the winds. And the Aeolians lived in this community, supposedly, and would stretch cables along the cliffs of their settlement and taut cables so that when the wind blew across them, they would cause vibrations that would produce sounds like that. So much so that as people were sailing, they would hear these sounds and not know where they came from. And so people would be like, don't go there. It's the Aeolians. They have monsters or something, right? And to us, it seems ridiculous. But in a world where there was no such thing as amplification, you couldn't plug something in and make it sound really loud. There was no amplification. All you have is sound that gets produced, and the amount of energy you put into it determines how loud the sound is. Well, enter resonance, and it turns out that's not true anymore. It's not just about how much energy you put into the wave. It's also how tuned the harmonic oscillator is to the particular natural frequency. So with no more energy than a simple periodic push, you can create massive amounts of sound, massive amounts of movement, right? And so when it comes to sound, this is one way that it happens. But there are other ways that this happens. I'm going to let you guys, if you want, you can watch the Tacoma Narrows Bridge. You probably have seen this before or heard of it before, but it's probably the most famous case of resonance. It's what happens when you go home. Uh-oh. After all these years, you got rid of this web page? That's terrible. So I'll just click on this because this is a quick video.
Live TV from 85 plus channels with local sports.
Yeah. We know YouTube.
Try it free.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So ponder for a second. Have you ever been on a road surface that moved underneath you when you were driving or walking? Can you imagine what that would be like? And this isn't just a little bit of movement. You're seeing like almost 45-degree tip. That's incredible. And by the way, it did this for quite a long time. And it was a joke among the community in Washington. They called it Gallopin' Gertie. And it was fun. You'd go out and drive your car across it on certain days when the wind was making it wobble like that. But it didn't end too well for the bridge.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
So you know it's not going to end well for the bridge, but I want to point out something. Anybody ever been across the Mackinac Bridge? You can feel it move a little when you go across it, especially if it's a windy day. But what's different about this bridge? Take a look at the bridge. What's different about that compared to the Mackinac Bridge? What do you notice?
They have the grates in the Mackinac Bridge.
This is a solid pavement, right? The Mackinac Bridge has grates where you can like look down and actually see right down to the water, metal grating. So air is allowed to pass through the roadway on the Mackinac Bridge, not on this one. The other thing that's worth noting, look along the side of the roads. What kind of railings do you notice?
Like solid girder.
It's just metal all the way across. There's no holes in that. This isn't like pipe railing like the Mackinac Bridge has, or any bridge that you will ever see nowadays has. And the reason for that is we learned the hard way. It turns out that the wind that was blowing across the bridge didn't have to be blowing hard. It just needed to be blowing at just the right speed, which was really close to the natural frequency of the bridge. And as the air blew across, it would create those little eddy currents that would push a little bit on the bridge as they broke off. And over time, you wind up with just the right speed wind producing resonant force. That forcing function of the eddy currents kind of pushing the bridge happened at just the right frequency. And you wind up with, ta-da, a collapse of a bridge. So bear with me. I got one more thing that I want to share with you before we skedaddle. By the way, that guy right there is one of the engineers of the bridge.
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
And a dog. There was a dog in the car. And it was the guy who was one of the head engineers for the bridge. He had driven and he was going across the bridge to go be with his family, and he stopped because it was really, really windy and it was starting to rock really bad. He got out of the car and was like trying to take some measurements, and then thought, I better get out of here. He left his dog in the car, ran for the edge, and the dog died. But what are you going to do?
So how long did the bridge last?
That's a good question. I think only a span of a couple of years. I don't remember, but it's incredibly famous. This is pre-Mackinac Bridge. This is pre-Golden Gate Bridge. Yeah, pre-Golden Gate Bridge. This was incredibly big in the realm of engineering. And if you think for a moment that engineers figured it all out and we've never had any problems since then, allow me to show you one more thing.
Yeah.
The bridge opened on the 10th of June, 2000.
2000, the year 2000, not that long ago. It is the Millennium Bridge in London. It's a pedestrian bridge. And what they discovered was everything was fine. The designs were perfect. They accounted for this breaking off of the wind. They accounted for all of that. What they didn't account for was walking, and people walking across the bridge and stepping in a particular pattern. And I'll kind of zoom to it here. The bridge wobbled back and forth. They shut it down. They did investigations, and they finally figured out the problem. And the main culprit was that the civil engineers who built that bridge never bothered to read a journal that was published not too long ago by some seismologists who warned that a side-to-side motion would also cause resonance in bridges. Had the civil engineers read the Seismology journal, they would have known this. But of course, why would they read a seismology journal? They're civil engineers. So it's a really interesting story. There's a video, you can watch that. I put these on there for you to kind of investigate, to take a look at these. The very last page of the notes is really just what can we say about the harmonic oscillator in these four situations. So this one I want you to finish up. I'll post a little answer key for this so you can check this out later. But this gets us to the end of 4.3, the end of chapter 4. And what you're going to do for next time is obviously finish up that last little page of notes. You have a problem set to work on. You can get as much done. If you have questions, we're going to work on the 4.3 classwork next time. We'll spend a little bit of time on the problem set next time if you have some stuff to finish up. And on Thursday, the day after next class, that's when you'll be getting the exam for chapter 4. It's a short one. It's only a 50-point exam, but you'll have from then through Sunday to finish that exam. So I know I'm kind of rushing, and I appreciate you guys giving me a couple extra minutes here at the end. But that's what's on the docket for next time. So get everything done for 8.1 and 8.2. Get started on those 8.3 problems on the problem set. Next time we'll focus on the 8.3 problems. We'll answer any questions you have on that. You'll have through the end of the day to be able to finish up those and get those submitted if you need to. So don't worry if you don't get them submitted before class. It's not the end of the world. So sound good? Okay. And I know I'm like, but if you have any questions or if you need anything, you can stick around afterwards and I can talk to you. I'm going to hit the stop on the recording here.